Here is our presentation video of our work, Faithful Extreme Rescaling, via Generative Prior Reciprocated Invertible Representations. Image downscaling is a typical way for efficient storage and data transfer. The capability of rescaling a low-resolution image to a high-resolution one is important. Therefore, different image priors have to be introduced to reduce the mapping ambiguity from low resolution to high resolution. Data prior is typically used in deep learning, which applies large-scale data to train a model. It is limited to 16 times upscaling. Data prior is able to maintain the overall structure of images but lack details. Some pre-trained GAN models have powerful generative capability, and generative prior searches for a latent code in the GAN space to generate the closest result. It can achieve 64 times upscaling, and the results are lifelike but not faithful. The above issue raises a question: can we enrich the informativeness of an extremely downscaled image to better incorporate with a generative prior? To answer this question, we turn to the invertible prior. Unlike previous works that separate the downscaling and upscaling processes, invertible rescaling embeds significant information into the low-resolution one, to help restore the high-resolution image. To activate different image priors under extreme scenarios, we propose a generative prior reciprocated invertible rescaling network. It is composed of 3 complementary modules: an invertible module, a generative module, and a decoding module. The invertible module encodes the ground truth image as a low-resolution image, and decodes it to restore a high-resolution image and invertible features. Our invertible module includes 3 parts: an encoder that embeds necessary information into low-resolution images, a quantization operation that simulates the process of saving images, a decoder that generates invertible features and high-resolution images. The generative module consists of code prediction layers and a pre-trained style GAN model. It maps invertible features to the style GAN latent space, and utilizes the pre-trained style GAN generator to generate a high-resolution image and generative features. The decoding module combines invertible features and generative features to generate the final faithful and realistic high-resolution image. The basic block consists of a squeeze and excitation module and several convolution layers for integrating and decoding priors from different resolutions. The default dataset is Celiba HQ, which contains 30,000 human face images. We first compare our method with GAN prior super resolution methods, indicating that our method succeeds in both verisimilitude and lifelikeness. Then, we compare with CNN-based super resolution methods, and the results show that we can generate more plausible details. In addition, we compare with invertible rescaling methods. Besides producing realistic high-resolution results, our method is able to output a perceivable low-resolution image. Table 1 presents a quantitative evaluation measuring different methods. As for the ablation studies, we try to remove each module of our framework to verify the effectiveness of the architecture design. Quantitative results are shown in Table 2. We perform experiments on face images collected from the web, to verify the generalization capacity of our method in real world. Besides human face domain, we also extend our method to various domains, such as cat and church. With different rescaling factors, our method can even restore an authentic background with clear textures, which is out of face domain. This experiment shows a visual comparison between our method and JPEG compression. Our method achieves a good balance between image quality and storage size. Our work can be summarized as follows: we propose the first invertible extreme rescaling framework, that allows perceivable downscaling and faithful upscaling. We design a reciprocal strategy, that elegantly connects the invertible prior with the generative prior. Extensive experiments demonstrate the superior performance of our proposed model against state-of-the-art rescaling methods. The style GAN may introduce undesirable biases, and it can be addressed by fine-tuning the style GAN model. In addition, the rescaling setting requires the high-resolution version of to embed information. It will be an interesting work to extend our framework to super resolution. Thank you for your listening.